Hi guys, Dr. Nunez here, and today we're going to look at the boundary behavior of waves. So to this point, we've learned a lot about wave characteristics. So things like amplitude, frequency, wavelength. We've learned about the wave equation, V equals F lambda, which is probably the most important equation for waves. Now we're going to look at many of the interesting things that can happen when a wave hits a boundary. So things can happen like reflection, the wave can bounce off, the wave can transmit, the wave can interfere, and so forth. So that's what's coming in the next few slides. One thing is important to note, the speed of a wave is determined by the medium. So if a wave goes from one medium into another, then we know that the speed can be affected. Whereas the frequency of the wave is determined by the source, whatever is creating the wave. So if a wave goes from one medium into another, the frequency is not affected. That's a really important piece. So frequency of a wave is not altered when crossing a boundary. The speed may be. So one of the things that can happen when a wave hits a boundary is that it can reflect. When you think of reflection, think of a wave bouncing. So reflect, bounce. Now in this particular case here, we have an incident pulse that's being sent down through a rope. The rope itself is the medium, and it hits a fixed end. So the fixed end is shown here. This means that it doesn't move. So when this pulse winds up reflecting at the fixed end, it inverts and moves back. So this inversion of the reflected pulse is due to the fixed end reflection. Now a few things about this fixed end reflection. In terms of speed, wavelength, and frequency, there is no difference between the speed, wavelength, and frequency of the reflected pulse and that of the incident pulse. They're the same. So the speed's the same because it's going through the same rope. The frequency is the same because it's set by the source. The wavelength is the same because V is equal to F lambda. The only thing that's different is the amplitude. There's a little bit of energy absorption at the boundary, and so when the pulse reflects back, usually it's with a lower amplitude. Here we have a free end reflection. The diagrams look very similar to the previous slide, but the difference here is where the rope attaches to this vertical support, there's a ring here. And so this ring can slide up and down and is free to move. So that's why we're looking at free end reflection. So we send this incident pulse down the rope and it reaches the free end, and this loop can move up and down. It's not fixed. And so when it reflects back, the reflected pulse isn't inverted. It has the same phase. So if you start with a crest, the reflected pulse is going to be a crest. Now, speed, frequency, and wavelength of the reflected pulse are all equal to that of the incident pulse. And again, the reflected pulse will come back usually at a lower amplitude because there is a little bit of energy absorption that happens at the boundary. At the base of this slide, you'll see a hyperlink to a YouTube video which shows some great demonstrations of fixed end and free end reflection. One of the interesting phenomena that we see with waves is that they can interfere. So interference occurs when two pulses or two waves interact in such a way to occupy the same space at the same time. So there are two types of interference that we're going to look at. The first is called constructive interference, and it occurs when two crests meet up and interfere, or when two troughs meet up and interfere. So if you look at this diagram here, you'll see that there's a red crest and a blue crest that are about to interfere, or they're moving toward each other. During interference, they are physically on top of each other, the red and the blue, and they add. The red has an amplitude of 1 and the blue has an amplitude of 1, and when they interfere, they create a pulse that has an amplitude of 2. So they act to construct on each other. They're building on each other. The same goes with these two troughs down here. When the red and the blue trough, both of amplitude 1, meet up, you wind up with a really big trough with an amplitude of 2. At the bottom of this slide, you'll see a hyperlink to a YouTube video showing constructive interference. With destructive interference, the two pulses, in this case, it's going to be a crest and a trough, they act to try to destroy each other. So if you look at this top left diagram here, you have a crest of amplitude 1 meeting up with a trough of amplitude 1 as well. And so when you superimpose the crest and the trough, both of the same amplitude, you wind up getting this green line here, which basically suggests that the pulses destroyed each other. What if the pulses have different amplitudes? Well, so down here you'll see a red crest with an amplitude of 1 and a blue trough with an amplitude of 2. So when they both superimpose, think of it as +1 plus -2. The trough wins by an amount of -1. So what you see during interference is a trough that has an amplitude of 1. Again, at the base of this slide, you'll see a hyperlink to a video showing destructive interference. So this slide is showing two waveforms that are superimposed, and we want to find out what the resulting waveform looks like. So since crests are happening at the same time for the red and for the blue, as well as the troughs, we can say that this is going to be an example of constructive interference. And the way to solve for the resulting interference pattern is basically you're doing math. So at any location, you're adding the displacements of the red and the blue wave. So I'm going to work exclusively with crests and troughs. And I'm going to make the resulting waveform in green. So at location C, right here, you'll see that the red has an amplitude of 2 and the blue has an amplitude of 4. So 2 plus 4 is 6. So I'll also mark the 0 locations. So at location G, you'll see that the red is at -2 and the blue is at -4. So you wind up getting displacement of -6. And that means we've gone through one full cycle. So we can kind of repeat what we've done here. And we'll see what the interference pattern is going to look like. So it's very similar. It's clearly constructive interference. There we go. We know what happens before interference. The two pulses are heading toward each other. We know what happens during interference. This is where the two pulses superimpose and either build on each other or act to destroy each other. But what happens after interference? This is a little spooky. It's like the pulse that you get during interference dissolves back into the original two pulses that continue moving past each other. So what's kind of weird is it's like the medium has a memory of the pulses before interference, and it retains that memory during interference. So after interference, those pulses are able to reestablish and move past each other. Standing waves are a really interesting phenomenon. They occur when you produce waves in a medium that travel down toward a boundary, and those waves reflect back and interfere with waves that you continue to produce to send down the medium. So you could see this like with a string. You have a string attached to a wall. If you send a pulse down, it reflects back. But as it's reflecting back, if you send a pulse down, they wind up interfering. So what standing waves are the resulting interference pattern that occurs between waves that you send down a medium and waves that reflect back. If this happens at the proper frequency, you wind up getting points of consistent constructive interference, which we call antinodes, and points of consistent destructive interference, which we call nodes. A standing wave pattern generally looks like this. Now this is showing you think of them as like photographs of a wave at various moments in time, and those photographs are all overlaid on top of each other. So at one particular moment in time, what you'll see is this red wave. okay? And then at another moment in time, you'll see the blue, and then the purple, and then the green, and then the orange, yellow, and then yellow, orange, and so forth. Point A is showing you a piece of the medium and how this particular point moves as this standing wave evolves. So point A starts up on top, moves toward the bottom, and then from the bottom it moves back to the top and it cycles back and forth. So this is called an antinode because it's a point of maximum displacement. Point B over here is called a node because point B doesn't even move, it just kind of stays still. So there's a hyperlink at the bottom of this page to an excellent video on standing waves and how they're generated. This brings us to the Doppler effect. Perhaps the best way to explain the Doppler effect is to consider an example. So let's say that we have a bug right over here, and it's in a perfectly still pond. It's resting on the surface. And this bug starts to kick its legs at a frequency of 1 hertz. And so that means it kicks its legs once every second. And it produces ripples in the water that move out in all directions. And let's say that we have an observer at point A and we have an observer that's at point B. And let's say that they're dipping their toes and their toes are detectors for waves that are kind of coming in. So each person at point A and point B will detect waves coming in at a frequency of 1 hertz, which is equivalent to the frequency that the waves are being produced. Now, let's suppose that the bug starts to move to the right. So as the bug moves to the right, the bug kicks its legs at a frequency of 1 hertz. And the waves that are produced have a smaller and smaller distance to travel to get to point B, and a larger and larger distance to travel to get to point A. What you find in front of the bug is that the waves are compressed. They have a shorter wavelength and they have a higher frequency. The person at point B with their toe in the water is detecting a frequency that is higher than 1 hertz. Meanwhile, the person at point A is detecting waves that have a frequency that's lower than 1 hertz and that have a pretty long wavelength. Meanwhile, the bug is producing waves at a frequency of 1 hertz. So the frequency detected at A, the frequency detected at B, and the frequency of production are all different. This is essentially the Doppler effect. So the Doppler effect is the apparent increase or decrease in observed frequency when a source is moving toward or away from an observer. We've all witnessed the Doppler effect whenever a car zooms on by. You can hear the roar of the engine. It's a high frequency roar. And as soon as it goes right past you, there's this Doppler shift. You hear like a shift to a lower frequency. So there's this high pitch shifting to low pitch as something like a source of sound moves toward or away from you. There are several great videos on the Doppler effect. The links are going to be put here on the page, so you definitely want to access these videos. There's even a Doppler effect for light, which is called red shifting or blue shifting. And this is something you may have learned about in 8th grade. When a source of light moves away from an observer, the color of the light is red shifted. Whereas if a source of light is moving toward an observer, the color of the light is blue shifted. So definitely check out the videos on this page. This brings us to resonance. Resonance is a really interesting phenomenon, and essentially what it is a frequency matching that occurs between an object and the waves that the object is exposed to. So every elastic body has a frequency that we call the natural frequency. So if you take a glass and you strike a glass with your finger, you'll hear a pretty sound that's essentially at a particular frequency. That frequency is the natural frequency of the glass. If we expose the glass to sound that has a frequency that matches the natural frequency of the glass, the glass is going to start to shake. And if it's done with enough amplitude, the glass will shake with greater amplitude, and it may actually wind up breaking the glass. So this is what we call resonance. Now, this is the principle upon which a microwave works. So water molecules have a resonant frequency. It turns out that it's in the microwave range, microwave being the electromagnetic wave. So when you put something in a microwave, the appliance, to cook, that food has water in it. And so when you expose that food to microwaves that have a frequency that match the natural frequency of the water in the food starts to shake, those water molecules. And that means you wind up heating up your food. There's a really famous case in bridge design called the Tacoma Narrows Bridge collapse, which happened in 1940. This was a bridge that collapsed a few months after it was built due to aerostatic flutter. Aerostatic flutter occurs when air moves around a large object, like something like a bridge, and it causes fluttering to occur at a particular frequency. Well, this happened with this bridge, and it turned out that the fluttering frequency matched the natural frequency of the bridge. And so it started to vibrate like crazy. So there's an attached video that you can watch, and you'll actually see the video of the actual bridge collapse. Again, this is a landmark case in wind-induced resonance. Diffraction is the spreading of a wave as it passes through an opening in a barrier. These diagrams here on the left and the right side are bird's eye views of waves coming in. The dark line here represents a barrier, and this is the opening in the barrier. And so you could think of these lines, these wave fronts, as being kind of like the crests of a wave coming in. And you would think that only this part right here would make it through, and it does. But you wind up getting spreading of the wave, and it's this spreading that is diffraction. So the wavelength is the distance from crest to crest. So this is our lambda here. And it turns out that if the opening is much larger than the wavelength, then you get a small amount of diffraction, or you get very low amount of spreading as the wave makes it through. On the right-hand side, you'll see that the size of the opening is much, much smaller. And so here, again, this is our wavelength, the distance from crest to crest. Here the wavelength is about the same size as the opening in the barrier, or if the opening is smaller than the wavelength, you get a lot of curvature here. You get a lot of spreading or a lot of diffraction as the wave makes it through. So if the opening size is much bigger than the wavelength, you get very small diffraction, or very small amount of diffraction. If the opening size is on the order of the wavelength, or maybe even smaller, you get pronounced diffraction, lots of diffraction. Check out the attached video to see diffraction being simulated in a ripple tank. This brings us to the electromagnetic spectrum. So we know that electromagnetic waves are special. They're the only wave that can move through a vacuum. They are not mechanical waves. And in a vacuum, electromagnetic waves travel at the speed of light in a vacuum, which is 3.00 times 10 to the 8 meters per second. Now, there are many different types of electromagnetic waves, and so we have a spectrum here. On the top part here of the spectrum, you'll see a wavelength in meters, and on the bottom, you'll see frequencies in hertz. And you'll see lots of different types of waves. So we'll start here on the left side with electromagnetic waves that have a large wavelength and a low frequency. So here are your radio and your TV waves, so largely used for communication. If you increase your frequency, you wind up getting into the microwave range. Beyond that, you get into infrared, which we as humans detect as heat. And then you get into this really small range here, which is the visible light spectrum. And this is a blown up view of this visible light spectrum. So you'll see all the colors of the rainbow here, Roy G. Biv. This is the wavelength in nanometers, so anywhere from 400 to 700 nanometers. And it's about 1% of the electromagnetic spectrum. And this is what our eyes are tuned to. It's pretty amazing how this is what we can see out of the entire spectrum, and it's good enough for survival. So then you have UV, which gives us nasty sunburns. Bees can see in UV. X-rays, which we know all about when you go to the dentist, or if you're at the hospital and you need to get an X-ray, you get exposed to these rays, which can show bone, or they could also show other features that are useful to doctors. So overexposure to X-rays is harmful, though. So you get an X-ray. There's a lot of benefit to that, but you don't want to keep getting X-rays because the overexposure is not healthy. Gamma rays are super high frequency. They're released by stars. There are some medical uses for gamma rays that revolve around destroying tissue. Things like tumors and various types of inoperable tumors in cancer can be treated using gamma knife. This slide's a great visual for showing you the frequency and wavelength associated with each type of electromagnetic wave. So you can see over on the left end over here, it's really hard to make out the cycles of the wave because the frequency is so high and the wavelength is so low. So this is your really high energy waves, your gamma rays, really dangerous stuff. And so you can see now that the wavelength increases and the frequency is decreasing as you move to the right. And over here, this is where you have your communication waves, your radio waves. And the wavelength is on the order of about 1 kilometer or thereabouts, so that's really big. This slide here just gives a summary of some of the things that we've talked about already with all the various types of electromagnetic waves. Now we will be looking at light in detail. When I talk about light, I mean electromagnetic waves. And there's going to be a unit or two specifically that deals with light, with reflection, with refraction, and that'll be coming soon. All right, guys, I hope you enjoyed this presentation. Let me know if you have any questions. All right, guys, take care.